Very good morning to everyone. We were dealing with the utilization of complete flow systems for the synthesis of APIs in an efficient and effective manner. This has not only been utilized for the synthesis of APIs, this has been also used in the stereoselective synthesis, where an organocatalysts are used, which is homogeneous in nature. Today's subject of discussion is continuous flow homogeneous stereoselective organocatalysis synthesis. The catalysts which we can use can be homogeneous, and in this, the homogeneous catalyst is added along with the reactants, which effectively catalyzes the enantioselective synthesis and create enantiomeric excess products. Here, the parachloro, R is chloro here, beta nitrostyrene was dissolved in toluene solution and treated with diethyl malonate, where R dash represent OET, in the presence of Takimoto bifunctional thiourea. This is the Takimoto bifunctional thiourea. It has thiourea and a tertiary amine. Because of the presence of these two functional groups, it can act as a both proton acceptor and a proton donor. Because of this unique feature, it's of bifunctionality and homogeneous nature. It can effectively carry out the catalysis of enantioselective synthesis. Both were dissolved in diethyl malonate, and this Takimoto bifunctional thiourea is a choice of catalyst for Michael addition reaction, 1,3 dipolar addition reaction, cycloaddition reactions, and so on and so forth. This has been used in 20 mole percent concentration. All these were mixed in toluene solution and pumped into the 400 microliter capacity PTFE tube, polytetrafluoroethylene tube. It is a type of Teflon coil reactor which is highly chemical resistant and also thermal resistant. It is having an internal diameter of about zero point 0.5 millimeter, which has been heated at 80 degrees centigrade for a period of 10 minutes. The stereoselective Michael addition takes place. Michael addition is addition across the carbon-carbon double bond, which is conjugated with an electron withdrawing group to give the R derivative, R isomer, when 81% enantiomeric excess with a 98% yield. What is the use of this addition product? This has been utilized in the starting material. This upon hydrolysis followed by decarboxylation in a continuous flow system, it gave R-baclofen. R-baclofen is the drug of choice for treating the severe muscular spasm of cerebral or spinal cord origin, which includes multiple sclerosis to traumatic brain injury. This baclofen synthesis has been achieved in quantitative yield by continuous flow system. Continuous flow system is not only utilized for the synthesis of various APIs or the API intermediates, but also can be used in a for the stereoselective synthesis. Many of the compounds are the racemic mixtures, and the racemic mixtures are of not of choice because these racemic mixtures are having opposite characters like quinine and quinidine. Quinine is an anti-malarial agent and quinidine is an anti-arrhythmic agent. Totally different types of activity. That's why continuous flow system has been utilized for stereoselective synthesis by using homogeneous or heterogeneous organic catalysts. This is the another utility of continuous flow system. Overall, this is the future of the not only the production of APIs for also for research purpose in the laboratory. It has its own advantages. Let us summarize the advantages of this continuous flow synthesis. As we have already seen that it has high surface to volume ratio, which is attributed to the tube system technology, where there is the large surface area and the ratio between the volume and the surface area is very high, which ensures the enhanced heat transfer and also mass transfer. Thus, the quantitative yields can be achieved, which is a far distant possibility in batch reactors. Micro reactors are the future of chemical synthesis. Though we are at the beginning stage, still there is a lot way to go. The reaction is extremely faster. Thus, the reaction time has been reduced to less than 1 minute. We have seen the examples of synthesis of rufinamide where we have been exposed the reaction for only 30 seconds. And there is increased safety. We are using in very small amount the starting materials. We know in the rufinamide synthesis we are using variable aryl azide, which is prone to detonation and it explodes. And in the normal batch reactors, handling is a very difficult task. In this, we are producing these azides in very small quantities. As it is produced in very small quantities, as soon as it is produced, it is utilized. And that's why the material usage has been as soon as possible it is utilized, and thus way it increases the safety. Not only it increases the safety, parallel scale up is also possible stepwise. As the reactors are in microliter capacity or few milliliter capacity, the consumption of reagents and solvent and energy is also reduced extremely and enormously. As it is used in an efficient manner, low waste is produced, and that's why management of it is also equally easy. The highly exothermic reactions can be controlled very efficiently because it is the microreactors. Cooling is more efficient. The high pressures and high temperatures can be achieved and maintained and managed in a better manner than the batch reactors. The possibility of explosion can be avoided. Possibilities of accidents can be also avoided, which is making more safer for the human beings and also to the environment. Highly toxic and corrosive reagents, highly reactive and unstable reagents. When the synthesis of rumphenamide, we have seen propiolate amide, which is highly toxic and corrosive reagent, which has been managed efficiently. As soon as it is introduced, it has been utilized, and it is produced in smaller quantities, and that's why there is better efficiency in the management of this kind of substances, which is a distance possibility in the batch reactors. Optimization of the reaction is easier and rapid, and the scale up can be planned parallelly, and miniaturization is possible. If possible, the atomization can also be achieved. Because of this miniaturization and atomization, it reduces the manufacturing cost, operating cost, and maintenance cost, which in turn reduces the power consumption and thus way leads to economic production of the APIs. It offers the possibility of combining the inflow chemical synthesis along with new analytical technologies like LCMS or GCMS and whatnot. And that's why the inline monitoring is also enabled. Thus, it speeds up the isolation and the purification of the chemical intermediates during the synthesis of APIs. Though it has many advantages, it has its own limitations too. Every product has its own limitation. Like we have our own limitation, every person has its own limitation. Why these limitations? If we do not have limitations, we do not pray to God for our survival. That's why as God has given limitation to each and every one of us. Likewise, to the instruments and equipments which we create. Let us look into the limitations of the microreactors. As the size is very small in few microliters, and if at all we use the solid material, the flow of solid material will be not so easy, and it may clog the and block the reactor, and the solid may precipitate during the process of synthesis, and this clogging is one of the major problems faced in continuous flow synthesis using microreactors. However, sophisticated technologies have been developed to handle these clogging problems to the major extent. Still, the problem exists. It is said that 50% of these reactions is possible by continuous process in an efficient manner. But however, 63% of these possible reactions cannot be performed through microreactors due to solid precipitation. That's why we have to use special solvents like N-methyl pyrrolidone, as we have seen in the synthesis of one of the APIs, which is water soluble and water miscible and also organic phase miscible. Still, the problem exists. Yet, it has to be solved. Each and every reaction is unique, and that's why each and every reaction has a unique problem, and we need a unique solution for the solving of that particular reaction problem. We use catalytic bed reactors, and continuous usage of this deactivate the catalyst, and frequently we have to repack, if not repacking, at least reactivate the catalyst which has been loaded into the catalytic bed reactor. This has to be done frequently. That is the another problem which has been faced in the continuous flow system of synthesis. And enantiomer compounds production is also the challenge. This is the future challenge, and we are still at the nascent stage. We have seen one example of preparing our enantiomer in enantiomeric excess form with 98% yield, but still it has to be explored. This is the area which has to be further explored. Though microwave reactors can be manufactured and technologies have been developed, the silicon micro reactors, glass micro reactors, steel micro reactors, or Teflon micro reactors have been produced, but still we are at the nascent stage. There's a very long way to go. The time should answer the problems which we can face and we can solve, and the challenges which we can face, and how we can solve the challenges, face that challenges, and achieve the synthesis and end efficient manner. Anyhow, continuous flow system is an emerging technology where we have lot of investment. Not only the investment, we have to invest our time. That's why it takes a longer process as on today, as it has not been as developed or as established as that of batch reactors. But however, this is the future of synthesis. Change is only the permanent thing in this world. Let us open up to these changes. Let us change with the time, with the changing time, and face the challenges and achieve the targets. With this message, I would like to end this presentation. Next presentation, we deal with the new subject. Till then, have a nice day. Thank you.